Welcome to SysD 16. I am your instructor, Rich Nguyen, and today we will cover a video lectures on machine learning fundamental. So let's get started. There are a few learning outcomes we would like to accomplish today. There are totally four of them. One is to get familiar with some basic machine learning vocabulary and fundamental concepts. We're going to take a look at a optimization procedure of a simple learning algorithms, and then we make some connection to the field of statistical analysis. And finally, we're trying to understand the model abilities for generalization. So here we go. First, let's talk about the quick overview of machine learning. And let's start with the definition. What is machine learning? Arthur Samuel, who is the gaming and AI pioneer back in 1959, had defined machine learning as a field of study that gives computer the ability to learn without being explicitly programmed. And that the definition pretty much stayed consistent throughout the years. And so you can think about it at a traditional programming. On this chart right here, you would feed data and the program into the computer, and hopefully that programming turn data into some of the answer that you seek. In machine learning, you change things a little bit. Instead of explicitly program to a computer, you feed it data and the answer. And hopefully, the computer would then do the programming itself. So that's the main difference between traditional programming and machine learning. As far as the timeline, machine learning exists starting from the 50s. And throughout at the artificial intelligence and a very exciting period of artificial intelligence. And throughout the year, the up and down machine learning, but they get really flourish in the 80s where other learning algorithms become more robust and we have more infrastructure to support machine learning algorithms. And not until the 2010s is where machine learning really take off with a revolution of deep learning. And with a lot of AI breakthrough that you see on the news or nowadays. So we are currently live in the third sort of period of artificial intelligence machine learning with the breakthrough of deep learning. So that's a quick timeline. And I'm sure you can think of some artificial intelligence, machine learning, deep learning application that you find most interesting. You might think about this is on the news, social media, magazines, or you may have learned it from a friend, but I want you to think about some application that you find most interesting. I'm sure you can come up with something that interesting to you. But machine learning is everywhere, right? You use it every day with the social media, Twitter, you sentiment analysis, any social media with you filtering spam for you. In transportations, machine learning is used to help control the flow of traffic, monitor safety, and recent development of self-driving cars, also a very exciting piece of machine learning. In financial services, algorithms dictate the majority of the trading happen in the financial service. Machine learning also used for fraud detections. I have a friend who worked at a bank in New York, and he said that most of the trading, he was a financial analyst, and he said most of the trading how happened at the bank are done pretty much by algorithms. In healthcare, machine learning have been used to diagnose disease, discover new drugs, and also been used in recent robotic surgeries. I myself involved a bit of a healthcare project using machine learning. Currently, we are working on a diagnosis of bloodstream infection. It's a part of one of the grant that I'm involved in, so I know it very much. Largely use machine learning algorithms. We also have e-commerce. Think about it as Amazon, be able to learn about your habit of buying and recommend the products that you need. And finally, for virtual assistants, you have one of the virtual assistants in your phone these days. And those virtual assistants are getting smarter every day with natural language processing, be able to help you in the day-to-day basics. So these are just, some application of machine learning, and I'm sure you can find a lot more in your in your own finding, but you can see this happen everywhere. So come back to the question of why you want to study machine learning. And many of us have many different reasons to study machine learning. And I simply just put a few reasons here, and you certainly can insert your own reason in the greens there. Many of us probably want to obtain a data scientist position at a company, and that's why you're really interested in this. That maybe define your career and even your future. Some of you may just curious and see how it works. You seem interesting, and you want to learn the inner working of machine learning. Some of you want to gain more ability to solve problem at scale, large scale problem, and it just happened to be one of the very good career, best career in the 21st century. So those are maybe some of the reasons. You might have your own. Maybe we can have a discussion about the reason for us to study machine learning as well. So as far as the machine learning landscape, it is very wide, and there are a lot of companies now involved in the development and research of machine learning. This slide is quite busy with a lot of companies here. You might recognize some big tech company. You also may see some startups that also started with simple idea and develop into part of the intelligent landscape. And on the right, you can also see the technology stack of machine learning. This would be very useful if you're interested in learning different technologies and how they interact with each other. In this class, we're also going to learn a few technology that mentioned here. TensorFlow, Keras, scikit-learn. We are talking about using Google Cloud to deploy our app. We're talking about using cloud platform. We're going to also use Keras and TensorFlow at the main programming, and which you will be able to write at your assignment. So many of tools that we use are open source. Later on at the end of the class, we're going to also use OpenAI or OpenAI Gym for reinforcement learning. So there is tool that you can use, and beyond this, there's so many other tools that you can use as well. So let's deep down a little bit into what define a learning algorithms. And I think the best definition probably from Tom Mitchell, who is a professor of computer science and also department chair of the machine learning department at Carnegie Mellon University. And in 1997, he gave a good definition about learning algorithm, which everyone is used to this days. He said that a computer program is set to learn from experience E with respect to some task T and some performance P. If its performance on T measured by P improve with E. So that's a bit of a mouthful, but let's break it down into what it means by T, P, and E here. Right? So let's talk about the task first. So the task in this definition is not the process of learning itself, but learning is a mean to perform the task. For example, if you want a robot to be able to walk, then walking is the task. Learning to walk is a mean to achieve that task. And task is described in terms of machine learning system as a process, example, which is a collection of features, and we typically represent it by a vector x, a multi-dimensional n-dimensional vectors x with real numbers. And there is many different kind of tasks can be solved with machine learning. I'm going to mention a few here. You probably heard it before in your other class. So we have regression. We're trying to predict some value from the data. Classification is when you try to give label or category to certain category that in your data. Transcription is when you want to convert from some media down into text. For example, speech to text or video summarization to text. Machine translation happen when you try to translate from one text level of text to another level of text, so one language to the other, such as English to Spanish, English to Vietnamese, English to Chinese, and vice versa. Anonymity detection is very popular when you try to detect any fraud in the financial industry, or detect in the assembly line that we detect some item that been defective. Synthesis and sampling is very interesting tracks of research in machine learning in the way that you can generate new data that is very real. It's hard to distinguish between real data and artificially generated data, and it's to the generative learning topic. But that's certainly a really interesting task. And finally, is the density estimation, when you try to estimate the true underlying distribution of the data. Now, talking about the performance of the algorithm, certainly when you develop a learning algorithm, you want to be able to provide quantitative measure to evaluate the ability of that learning algorithms. And depending on the tasks that you have, you might have different performance here. For example, if you work on classification or transcription tasks, then the performance measure P should be accuracy or errors rate. When you're working on regression tasks where you're trying to predict some value, then the performance should be use mean square errors. And when you try to do the density estimation task, then you may use something like average log probabilities. So it varies depending on the task, and we only interested in see how the learning algorithm perform on data that I've not seen before. And this data are called the test sets. So when you evaluate performance algorithm, that's where you evaluate, not on the training that you use to do the training of the algorithm. Speaking of training, let's talk about the experience that Tom Mitchell was mentioned. So the learning algorithm was allowed to experience a data set, which is a collection of examples or data points. Sometimes we call this example, sometimes we call it data points. And depends on the kind of experience the algorithm allowed to have during the learning process. They can be broadly categorized as unsupervised or supervised learning. Now, there is also some learning algorithm not only just experience a data set, but they also interact with the environment. And so there is a feedback loop between the learning system and their experience. So such algorithm would be called reinforcement learning. So if you had to divide learning system into a broad category, you can define it as supervised learning algorithm, where you get provided the data on also the label associated with the data. And the goal of your learning algorithm is trying to learn a function to map from the data X to the label Y. An example, and I typically use this sort of a Apple example, is if you're given an image or an object, you need to recognize if that is an apple or not an apple in case of the classification. Now, unsupervised learning is when you only provide it with the data X and no label. And your goal is trying to learn an underlying structure of this data. So instead of trying to recognize this apple right here, I'm just going to say that this image of an an object, it look like another one that I seen, but I'm not necessarily had to say this is an apple. Right? I don't really was provided with the data saying this is an apple. And finally, the reinforcement learning is when you be provided with the state action pairs at your data. And what happened here is that you, instead of trying to provide label or to learn a function, you're trying to maximize a future rewards of the system over many different steps. So an example of reinforcement learning would be, in this case, if you see an apple, you should eat it because it keep you alive and keep going. So that's the action you had to take upon seeing an apple. So that is three type of different category of learning algorithms, and so the taxonomy of machine learning can be break down into these three broad fields, subfield, and depends on different category. You may see more even smaller subfield between it. So supervised learning can be break to regression and classification tasks. And within classification, you can see flaw detection, diagnosis, customer retention, image classification, and so on. I circle image classifications here because that's my main interest in machine learning, and I've done most of my research on image classification. But there's so many other fields out there that you would fit you're interested in, and it's very exciting that hopefully in this class you will be able to touch some of the application on these taxonomy. Great, so that's number one about the overview of machine learning. Let's talking about how to build a learning algorithms, right? And we'll start with a simple example, and this is the data that I take from the California housing dataset. And so the idea, the problem here that we have is if you provide it with different type of features or properties of these housing, can you predict the value of the house, right? The house here in the district, so you might see of the data appear a bit strange. So say total number of bedroom, you can see these the number of bedrooms, and sometimes the number is really high, like 100 to 1,000. Keep in mind that, it's always interesting to look at the data to interpret it as the machine learning engineer. And, you should be able to explain these data. For example, total bedroom here are not based on a single house, but rather based on the district that includes. You think about it, it's like a neighborhood. So those are the total number of bedrooms, they add up, right? And you may have other features here, like population, household, median income, so on and so forth. And your task is trying to predict the value of the house. And of course, this provided in table form, which is what we typically see. And we need to be able to translate this into a vector or matrix form, so that we can establish a mathematical foundation for machine learning. So by convention, we call the feature vector X, which is a data point with multiple feature, columns there across the board here, and each of these will be a single observation or a single data point in your data set. So that denoted by the superscript numeric, and you can have also associated label, which in this case denoted at Y, so superscript 1. And for each example, you have a corresponding label. Right? So you have total M would be typically denoted at the number of example or training or a data point in your data set. And if you look at the column, each of these will be the full feature. So you have the first feature with total bedroom, second feature a population, so on and so forth. And typically we denote the number of feature by subscript from 1 to n. Right? And if you look at the columns here, all the value, how value can be denoted by a vector, which contain all the value of in the data set in a single vector Y. And all the features can be represented by a capital X as a feature matrix, represent all the data that we have. So that's how you can convert from the table form to a more vector or matrix form. So our problem is, how do you design a learning algorithm such as the linear regression algorithms here, so that we use the training set that we have, and this algorithm would produce some hypothesis. A hypothesis H here is just a function taking an input value, which is X, and then produce or predict a value of Y, right? And for the linear regression, we use a simple model called a generalized linear model. And if you look at here, each of the features are represented by a number X subscript here. And we also have a associated parameter, so theta, which is the linear combination of different features. So what happened here is when you have an input come in at x0 to all the way to xn, and you associate with each of these input to a parameters, you can do a linear combination of these parameter and come up with your functions, right? So these are the generalized linear combination. Now, you can rewrite this a little bit to make it more compact into more vectorized form. So the prediction, typically the prediction would have a hat on it. So this case, y hat would be given by the hypothesis functions, and it is just a dot product between the parameters theta and the input x, right? And each of these parameters and input is a vector of size n plus 1. And you may ask, why is n plus 1? So the reason for that is we have this theta 0, x0. And x0, the value of x0 always equal to 1. So it's, your feature started at x1, like you see on the previous slide. But we have x0 here to make maybe the math framework more compact. And you can think about it a single value of theta 0, because x0 is always equal to 1. But make our math a lot more compact, because we can rewritten it at theta transpose the x here. So later on, we're going to see how this really help out when you do analysis of the learning algorithm. But for now, think about it. X0 is only 1, and theta 0 is sometimes called the intercept term that you basically ship the model up and down. Okay, so for the performance measure of this learning algorithms, or the P part of the learning algorithm, we choose mean square errors, or MSE, right? So MSEs are given by this formulation. And to explain it, it's really simple. It's just the average, right? So this is the sum, and then you divide it by all the number of training examples. So this is really just the average. And what kind of average is that? It is a square errors. Square here, and the errors are defined by the predicted value, which is y hat of a instant I, divided minus the actual label or the actual value of that instance, right? So you have feature matrix, label vector is the input of this MSE function, and you have prediction, you have the label, take the difference, square it, and then sum it up, and then average it, right? So that's MSE. And what important is MSE also represent a Euclidean distance, or square norm, between the prediction and the target. So in terms of vector, these are just the difference between the two vector square, and you take in the average of it, right? Now, to find the optimal parameter for this model, we can try to minimize these errors, right? Of course, the point of machine learning, we try to model well this data set, and the way we do this is we try to minimize this mean square errors. Right, so we want to make the prediction as close as possible to the label. Right, so how we do that? We minimize this error by solving for where is gradient equal to 0. Right, so the gradient MSE on training data must be equal to 0. Right, so you want to minimize something, always set the gradient equal to 0. Right, recall from calculus. So how do we solve this? Like, we know that the gradient of this mean square error have to be 0, or the Euclidean square distance have to be 0, the gradient of that square distance. So you can substitute the prediction by x thetas here, because that's how you calculate the prediction by the definitions of the generalized linear model. And then you can expand the Euclidean norm into x theta minus y transpose dot product of itself. And you can see if you multiply these terms out using linear algebra, you have these expressions. Notice that these are quantity of 2, because they actually have 2 terms of theta transpose x transpose y here. So you combine it into a quantity of 2. And then you want to do some gradients here. And think about gradient in calculus before, we just doing partial derivative with respect to parameter theta. In this case, if you see this term going to become, think about it at this, you have 2 terms of theta. So when you take in the partial derivative, you bring 2 out, and then you have a theta left. And then this term, you're going to drop on the theta when you take derivative, so it's end up with 2x transpose y, and the last term have no quantity of theta in it, so it would be dropping out completely when you take partial derivative. So you take this quantity equal to 0, and with a little bit of arithmetic, you can isolate theta. Now theta equal to this inverse time x transpose y. So by doing some math, we can isolate the parameter of the system, and this will be the optimal parameter to minimize that MSE that we want for the linear regression. So typically these will consider a beautiful thing that you can actually do this by yourself. Most of the time, you can't really do this closed form deviations of the parameters due to various reasons, more complicated, sophisticated challenges. But sometime in this simple linear regression problem, you was able to isolate by doing some math. You were able to find the optimal value of the parameters for your model. Now, if you look at this in sort of a graphical sense, these are all the point of your data, and your task were trying to fit a linear model, right? So we talk about the linear regression model here. This will be the best fit line to your data that we're trying to find, and this best fit lines are parameterized by theta that we find earlier, right? And if you look at the cost function or the MSE space, it can be represented sort of a nonlinear or quadratic curve, and our goal, we're trying to minimize this, find the minimum of this curve, which is happen to be the lowest points here when is a gradient equal to 0, or in this case a partial derivative with respect to theta 1 here equal to 0. So you find the minimum point there when you look at the tangents here equal to 0. Right. Okay, all right, turn on my pointer so you can see the red. Cool. All right, so most of the time you actually cannot derive the closed form optimization that you see earlier. So we need to employ an iterative optimization technique to find the optimal solution. So in this case, the core idea of iterative approach is trying to tweak the parameter iteratively. So what basically you want to alter the value of theta slowly, trying to minimize the loss function or the MSE bit by bit, right? And typically this step are defined by a learning rate. Learning rate basically say how large of each learning step should be, and we're going to talk about that in a little bit. So to look at more graphically, you can imagine this cost function represented by a quadratic curve, and the axis is represented by parameter theta, and the y-axis is the cost. And then our goal is trying to minimize the cost, right? So what happened is we're going to get to bottom of this curve, and we don't know where the bottom is, right? We can start at some random value for theta, and what we're going to do, we're going to move slowly toward that bottom, step by steps. And what happened, the way we're going to do it is, you can think about it, it's like you are going downhill, right? You want to go downhill as low as possible. So that's what give rise to the word descent in the optimization technique called gradient descent. And so when you do this in 1D, what happened is you want to go always go downhill, but if you look at it at a 2D, you can feel like you are doing it more in a mountain range, and you want to go downhill at every step. So what happened is, at every step, you look around you, right? So if, for example, if you look at this at 2 parameters instead of 1, then now you have a 3D cost functions, and you want to find the minimum of this cost function. On this case, the 3D surface, you want to go lower and lower until you can't go lower anymore, right? So iteratively, you try and update the setting of the parameters so that your cost function will be a minimum. Okay, so you can think about the gradient measure is like how much the output of the function change if you change its input a little bit. And this definition, informal definition from Lex Fridman from MIT. So typically I like to think about it is like descending from the mountaintop way down to the valley. Right? So how do we do that? We have an algorithm called batch gradient descent to help us find the lower the value of the cost function. Right? And the reason it's called batch is because you are the training data. So we're trying to calculate how much the cost function would change. It would change the parameter a little bit, right? And when you change the parameter a little bit, you know what that means. It means you take in a partial derivative with respect to that parameters. So if you need to think about the mountain descent analogy, it would be, what is the slope of the mountain if I take the step to the east, and then you do the same thing with take to the south or direction, and then pick the steeper descent. So in this case, I'm showing you an equation. I'm going to explain what it means here. So you can start with some value of the parameter theta, right? And then you're going to iteratively update it. So it's going to be assigned to some version of itself. But for this one, you're going to do a couple of things. You're going to consider the cost function, right? So you're trying to minimize the cost function. And you take in a partial derivative here. Basically, you're trying to find the slope of that function at that particular setting of theta, right? So think about it. If you here, you were trying to find a slope here. And remember how you find the slope there, right? So you can think about the slope is the tangent line to the curve at that point, and you can see the directions of the slope. So in this case, if you here, the slope here, you have a negative slope, right? So you have a negative slope here. And what happens if you want to minimize a function, you need to take the opposite direction of the slope, right? So in this case, if you have a negative slope, you need to take the positive direction in your parameter. So the positive direction in this exit is to the right, right? So you're going to move to the right. Here, negative slope, move to the right, you end up with another step. So you update this here, you have another value of theta, right? So that's explained the negative signs here, because the negative sign mean that you want to move downhill, so you want to take the opposite direction of the partial derivative. Partial derivative basically just the slope right there. So because if you here, you keep taking the slope, it's still a negative slope, so you take in positive direction, which is help you moving downhill, right? And the step that you take here basically defined by this learning rate, eta here. And you can define how big of the step you want to take to go downhill. So this formulation will help you explain that a little bit to see how it's actually quite simple, right? You keep updating the parameter so that you get a lower value or lower setting of the cost function. Right? Okay. Now, we have this formulation from last slide, and the J that you see here, because we evaluated a single parameters here, but you can think about the theta can go from 0 to n, so you actually go, oh, well, you don't include 0, then they go from 1 to n, so you need to looking at this as partial derivative for all of the features here, right? But to keep the simplicity to explain it, I start with a single value of J, or single dimension of J. So if you plug in the cost function, basically it's an MSE. You plug in the MSEs here, square loss, and then you take in partial derivative with respect to theta J. So you would take in the derivative with respect to theta J, you end up with these terms. So if you do a little bit of a calculus, you bring down the square terms. And remember, this is another, you had to do a change rule here. So you had to also take in derivative of that quantity after bring down the 2, right? And the derivative of this term using change rule, really interesting, because this, you think about this, is a weighted sum. And when you take partial derivative with respect to a single parameter in this vectors, only that quantity stay, and then the rest kind of go to 0. So you end up with also a J term of the vector X. So that's why it's there. I mean, you need to explain it using change rule, and you take derivative of that one, and only the at j term of x of I, right? So that's why the term is there. Okay. So next you need to look at not only on one direction, but also all other directions. Basically consider all of the dimension of the parameters data, right? And you evaluate on full training data sets. So if you look at a single dimension here, you have some term, but now you're looking at multiple dimension from 0 to n, right? So each of these, like we showed to you from previous slide, give you some terms here, right? And the only thing that different here is the lat terms with the change rule. So you end up with surviving different dimensions of the data, right? So you end up with this shoe vector like this, and you can rewrite it using linear algebra, some more compact form using the matrix form. So all the term going to become X transpose, and you have inside of this parenthesis, when you combine these or vectorize this, it becomes just X, matrix multiplication X and theta minus the vector Y. So the gradient can be represented at this quantity, which is kind of helpful to us because there's a nice compact form that we can use, right? So if you think about it in all dimension of the parameters, so this vector parameter theta will be represented at an iterative approach to taking some learning step using the gradient of the cost function, right? And you only just derive the gradient of the cost function j in this terms, right? So that's really all that is, right? So because now you can use that to update the new value of theta that reduce or minimize the cost function at that time, right? So how do you code this up? Simple enough. A lot of math that we're going to use in this course going to be directly from the formulation, and sometimes you will have to code this up using Python, using Colab Notebook, programming assignment, so on. You have to implement something. So here I'm just going to provide you some code to give you an idea of what the coding will be like. So you have some parameter eta here to define the learning step. So you have eta here. You also have number of iteration, because remember this is an iterative step. So you keep updating theta until you arrive at the minimum. Think about it, it's a multiple step. You keep taking to downhill until you can't go downhill anymore. So you can set this at some hyperparameter we will talk about. And then, M is the number of training example exists in your data set. So you set it you know this in advance, how many training examples you need. And originally you set theta at a random numbers, right? So all these initial setting of theta will be random. And then you kind of, these steps are basically implement this equation right here in using NumPy and using the linear algebra package from Python. So you might be able to implement something like this translate directly from the formulation to the code. Now, many of the concepts we're talking in class will be in the formulation, but at programmer, we all can translate the formulation into code. Now, the one problem I didn't talk about last time is how slow that batch gradient descent can be, because for each update step, you actually use the entire training set. So you might slow down the process. So one of the alternative is, instead of using the entire training set to update your parameter, you will pick a single random example in the training set and do the update. So certainly use single one a lot faster. However, it's sort of a random nature. So, your final parameter might not be arrived at the exact minimum, but bounce around a little bit, which is fine, but sometimes not optimal, right? So this is a sort of, you can think about the cost function at a bowl, right? So the function kind of dig deeper into the slides here, and you kind of keep trying to go downhill from there. You might stumble a little bit, right? So every time you use a single training example, but you will get there to the minimum point eventually. But if you use stochastic gradient descent, then you can implement it at a single training example, like I show you here. So everything mostly stays the same, but instead of using the entire matrix here, you would use just a single example, right, to derive your optimal parameters. Okay, or we can find a middle ground. So the middle ground would be not only select a single example, but instead using a small random subset of example, typically 10 to 100 in size, and these are called mini batch. So these are the version of gradient descent called mini batch gradient descent. And typically that what we use sort of utilize the best of both worlds pretty fast, but you don't have to rely too much on any single training example. Right? Now the hyperparameter learning rate was also pretty important here, because then you can look at how your algorithm would behave, and depend on the learning rate that you set, and these are just numbers that you set out to tell the algorithm how fast it should descend into this cost function. Now if you set the learning rate too small, each of these lines represent a configuration of your model, or a setting of the theta, right, vectors, and you can see that it's slowly convert to the best fit line here, right? So that may be too long for you. So sometimes you want to set the learning rate a bit higher, so you take a faster steps, right, to convert to the best fit line. But sometimes you're not careful, you set it too high, and it would end up missing the line. So what happened? It keep jumping back and forth with the settings. So choosing the learning rate will be an important task to be able to convert quickly and not overshoot the optimal solution. Cool. So the next thing we'd like to talk about is some connection to statistics, and this is fairly heavy on math. So I'm going to go over this fairly quickly for you, but to keep in mind that you might having some connection would be really helpful. We can gain some insight into the statistics. So the statistic we talk mainly about is the maximum likelihood estimate, which is one of the most powerful estimates in statistics. And many of the optimization in machine learning is interpreted at the maximum likelihood estimators, right? So let's consider a probability of X given theta. So you can think about this is at you want to maximum the probability of seeing the data given the parameters, right? So P of X given theta would map any configuration of the model to a real number that estimate the true distribution of the data, right? So you want to maximum the probability of observing X given our setting or our model. So the MOE for the parameter theta is defined at the maximum value for the probability X given theta. And typically X is a training set, so this consists of many different training examples. And so you have to break into a product of all of the training example, right? So be a product of training example from 1 to m. These are product of these probabilities. So typically we don't want to deal with product in probability because there's too many of them. So one of the strategy that we can do sometime is taking a logarithmic of those probabilities. So you end up when you're taking logarithmic, the product become a summation. So you can take log of p and then sum them all up. Let's be similar. So it doesn't change the maximization problems here. And the last thing we do is that instead of maximum, sometimes we choose to minimum. And maximize something is the same thing as the minimize of the negative quantity of that same thing. So you have a negative log here. So sometimes you refer to this as a negative log likelihood at the estimation. So if you run into that term, know that this is where it's come from, right? But it's the same maximization, minimization problem with negative log likelihood. Another one that's really interesting is, how do we justify the U of MSE at a cost function for our learning algorithms? And this is have connection back to the conditional log likelihood that we see. So to predict a value y given data x, so sometimes we can do is you trying to maximize the probability of observing y given x and some parameter theta. And this one, again, you can rewrite it as the sum of the log likelihood, right? So individual data points. And for the linear regression model, we model the conditional probability y given x at a normal distribution, with the mean is the predicted value and some variant sigma square that you can define. And if you plug in the formulation of the normal Gaussian distribution, this is what you have. So your MLE would be provided by this formulation. Now you can using some math to extend it out to these terms. And what really interesting you should look at is this last terms here. And if you look at it closely, you can see that in sample, the log this log likelihood would be similar to the MSE that we seen earlier, right? So that definitely kind of the very similar terms here. And even though the whole term kind of different, the optimal point was actually the same for these two terms. So you can see here, this is how we justify the use of MSE at a maximum likelihood estimation procedures. Right? Now, many of you probably taking Gaussian Bayesian statistics as well, and we use the use of maximum a posteriori estimation, and we can also draw some connection between the map estimations here and the MLE. So given Bayes rules here, the probability of theta given x going to be equal to this quantity using Bayes rule, and this is proportional to the probability of data x given theta times the probability of theta. And the map estimation will be the maximum maximization of this quantity, right? And if you break it out, the product going to be the sum of two terms here, log probabilities, log likelihood, and then you can break it down to product of number of training example. And keep in mind that this is going to be just a constant in our terms, and this can be a sum of log likelihood. And so for the maximization with respect to theta here, it can reduce to this term, which in turn is the MLE estimate. So this one, what it's telling us is that MLE is a special case of map where the prior is uniform. Right? So we not really go deep into this, but you see some connection between statistics and our own method. All right, the last thing we'd like to cover here is the model generalization ability to unseen data, which is very important for any learning algorithms. So the generalization is the ability to perform well on unobserved input. And the error that we measure on the training set is called the training error. So typically we try to estimate the generalization errors, which is testing error, by measure its performance on some test set. So we have one little assumption that we had to make when we divide this into testing and training errors, is that we assume that both training and test sets are generated by the probability distribution over the data set called the data generating process, right? And this process are assumed to be independent and identically distributed. This is an assumption called ID assumption in statistics, to make sure that both of our data set are drawn from the same independent and identity distributed distribution. Right. And part of a factor determine how well the machine learning algorithm will perform will depend on two factors. Number one is the ability to make the training error small. Right. You won't have to reduce the training errors. MSE part of it, make it small. And the second one is the ability to make the gap between the training and the test error small. Right. If you do these two things well, you have a good learning algorithms. Now, these are mapped or correspond to two central challenges in machine learning. The number one, mapping to a underfitting, would mean that the model are not able to obtain a sufficient small training errors, which is correspond to the first point, right? And then the second one is overfitting, is when the gap between the training and the test error is too large, right? Then we have overfitting. So many learning algorithms, we always try to balance between not too much overfitting versus not too much underfitting, right? So and the way we can control this, whether overfit or underfit, is changing the model capacity, right? Now, what is the capacity of a model? Is ability of the model to fit a variety of function. So model with low capacity might struggle to fit the training set, while model with high capacity may overfit by memorizing the property of the training set, and so therefore would not be generalized well or serve well on the test set, or this is a case of overfitting. So you need to control this capacity by choosing his hypothesis space. And let me show you how this is work in our linear regression model. Right? So in the case of underfitting, you can see. Let me move my mouse away. You can see that the estimates are done by a simple linear regression, which is just a line. Now, if your data set is a bit more complicated than a line, then this model is simply not good enough or is underfit the data set. What we need is a more nonlinear or quadratic model, right? So you can have this term x squared that you see below, the x0 squares there, for square term. So this is make the model capacity slightly larger. Now we support square terms, right? Now keep in mind, it's still a linear regression model because all of the theta is still a linear combination of the feature, even though the features now is a square, right? Now, if you rely too much on expanding the model capacity, you might run into overfitting. So in this case, instead of expanding into square, you expand it all the way to the 9 polynomial, would make the model very complicated. Now, it still fit the data that you see very well. As you see here, this 9-degree polynomial will be able to fit the data perfectly, but it's not really a good representation of the true data. So therefore, it's overfit to the training set, and therefore it poorly generalized to the test set. This overfitting can be represented really nicely in this figures here. The blue is the training errors. So you can say as you expand model capacity, the training error is going to reduce because the model now it can really memorize all of these training example. But the generalization error not necessarily going down, right? Because you overfit to the training data. And the other term is when you don't have enough capacity, so your training error is still high, so you definitely underfit, right? So the point of learning algorithm is to find the sweet spot here with the optimal capacity so that you won't overfit and you won't underfit. Another way for algorithm to perform well is that we give it some preference. To prefer one solution over the other solution, even though both solutions are eligible, right? So one way that we can make sure that we don't exceed the model capacity is trying to put some constraint on that model. And one of the constraints could be the L2 norm for the weights, and this is what we call regularizer, right? So before we try to minimize the term MSE on the training data, right? You try to minimize that term. We can also added an extra terms here called regularizer, trying to control the model parameters, right? So what happened here is that we have this term here and we're trying to minimize it, meaning that we want this parameter to stay small, right? So that part of the cost function we're trying to minimize. And the nice thing about this is that if you have this term, you can extend the capacity of your model in general. But through the training process, if this is included, it's also trying to minimize the product of these weights, and it trying to keep it small, right? So what happened is, even though you have a complicated model, you would end up with some minimum setting of lambda here. Lambda here just trying to say how important is my weight decay in my model. And so the setting of this determine like how big you want your model to get, right? You don't want to have it too big, which is when you set this to a small value, then this can allow to get big. Or you set it into too big a value, then this will be very small when you're trying to do minimization. So either way, you either underfit or overfit. So you have to find the value of lambda here to make an appropriate model, right? So what happened here is that the part of this lambda is also called the hyperparameters, is something that you set to help with your regularization. And there is many different regularization you can add, but in general, the regularization intended to reduce test error while not increasing the training errors. So testing and validating, the hyperparameter that you see earlier is a setting that you use to control the learning algorithm behavior, and it is separate from the parameter, which is part of the model itself, right? So there is a difference between the two, between the hyperparameter, which you use to control the learning algorithm behavior, and the parameter, where it is part of the model. So you need to figure out the value of these hyperparameter, and typically you don't train it directly. You find the value directly on the training set, because many of the time it will be causing overfitting. So you need a separate set called the validation set. So typically you can split your data set into 3-part: training set, obtain training errors. You can do the validation set to avoid overfitting, and you have a test set to obtain generalization errors, right? So it's good practice for you to keep the data set in 3 parts. And sometimes the data set is small, then you can use technique like cross-validation when you split data to complementary subset, and then train model on different combination of them, and then take an average, and then measure the generalized errors on the holdout test, right? So some of you may already familiar with this technique from statistics class, perhaps, right? So let me summarize by adding a recipe to build your learning algorithms. So many machine learning algorithms can be described as an instance of a very simple recipe. You're going to need 4 things. Number 1 is you need a representation of a data set consisting of the data X and some label Y. In the unsupervised problem, there'll be no Y provided. Second, you need a cost function. And the cost function that you see earlier, like the MSE or negative log likelihood, you can need some term for the statistical minimization or estimation. And you can also include some regularizer terms in there, so like the L2 norm terms for the parameters. Then you need an optimization procedures. And this can be done in closed form that I show you with the normal equation, or it can be done iteratively, like the gradient descents. So you need one of those optimization procedures. And finally, you need some specification for your model. So set the model capacity, whether it needs to be Gaussian in the linear regression case, whether it be linear model, non-linear polynomial models, and so on and so forth, with some specification to your model, such as capacity. Right? With all these 4, you can replay different components of these recipe, and then you can end up with a wide range of algorithms. So keep these 4 things in mind when you're moving forward. It may be very useful for you to design some learning algorithms. Now, I'll only touch on a no-free-learn theorems, and many of us may be saying that the goal is trying to design a machine learning that can solve all the problem, right? But in fact, in practice, it's very hard to achieve this general purpose algorithms because of the assumption that we make. Keep in mind that the model is just a simplified version of the data, right? So it's basically trying to determine which part of the data to keep, which part of the data to be discarded. So it have to make some assumption. And for example, in the linear regression problem, we make a linear assumption. So David Woodford in 1996 making a NFL theorem or no free learn theorem is that if you make absolutely no assumption to the data, then there's no reason whatsoever to prefer one model over the others. Right? The only time the model work is that because you make some assumptions, right? So for some context of the problem, you may be able to make some good assumption, and then you have a highly specialized algorithms, but then it won't perform as well as the general purpose algorithm on other problem, right? So it no best size fit all here, right? Typically, you have to make assumptions, and when you make assumption on the specific task, your learning algorithm may not be performed well on other tasks that it need to be done. So it's hard or very difficult to have a general purpose learning algorithm because of the assumption that we make. And you might see this apply onto the deep learning later on that we cover as well. But the best way to know what model is the best for sure is trying to evaluate them, right? So if you, you in practice, you can make some regular reasonable assumption and then evaluate a few reasonable model. Let me also mention a caveat of machine learning algorithm is the curse of dimensionalities. And so what happened is that many machine learning problems become exceedingly or exponentially difficult when the dimension of the data is high. So think about it. You can visualize data lying in 1 dimension, 2 dimension, and 3 dimensions here. And what happened is the complexity or the configuration of the model become exceedingly exponentially more difficult at the number of variable or number of feature increase. And the reason for that is this is simply a statistical challenge when the configurations become much larger than the number of training example that I've been provided. So what happened is if you look at this grid block right here, many of these grid cell will be empty, which means that there's some configuration of the model that have no training data to support it, right? So many of the simpler machine learning algorithms fail to scale to this statistical challenge. And then it would have a difficult time generalizing to the complicated AI level tasks. So we're going to look into it a bit deeper, but keep in mind this is one of the main reasons why deep learning will be very successful, because it was able to make some assumption about the task to overcome this curse of dimensionality. But we will leave that for a later discussion. So for this lecture, in summary, we should learn about some fundamental concept and some basic machine learning vocabulary. We took a look at the optimizations of a simple learning algorithms. We make some connection to the statistical analysis as a field. And finally, we try to gain a better understanding of the model ability for generalization. So for your discussion, which is happen right after this video, is that you're going to get a chance to describe the trade-off between the bias and variance, which is a very important concept. And, I'm going to encourage you to start by reading the deep learning book on section 5.4.4. You will also encourage to do some research on your own before posting on Piazza on your perspective. And hopefully we will come up with some interesting discussion, follow up by this lectures, right? So finally, I want to leave you at this note. If you want to take a really good sense of the landscape machine learning, just take a look at the competition that's happening in Kaggle currently. And Kaggle is a really realistic way that access what work and what doesn't. So if you got the time, go on Kaggle.com and then take a look at what competition going on right now. And there is a trend on Kaggle right now that is starting in 2016. It started dominated by two main approach, and one of the approach was using deep learning for perceptual problem like image classification. So just want to give you a bit of a tease. We're gonna on our way to learn more about deep learning, and I'm very excited now that we covered the basic machine learning. We can go on to learn more about deep learning. So brace yourself. Deep learning is coming. I'm a Game of Thrones fan, right? So I'm gonna leave you at that, and we'll see you in the next video. We'll learn more about deep learning. Thank you and take care.